something, I'm not sure. It's a reasonable open question.
Thank you.
Thanks, Adnan.
Thanks. Let's thank the speaker again.
Okay.
So the next talk is on fast mean estimation with Sub-Gaussian rates by Yashwanath Cherappanam-Jerry.
Hi, I'll be presenting on our work on fast algorithms for mean estimation with Sub-Gaussian rates. This is joint work with Nicolas Flammarion, who's a postdoc at UC Berkeley, and my advisor, Peter Bartlett. So the setup for the talk is like really, really simple. You're given n IID random vectors in R to the D with mean mu and identity covariance. And your goal is to produce a high probability estimate of the mean. So what I mean by that concretely is as follows. So you're given a target failure probability delta, and you want to design an estimator mu hat, which is within a radius r delta of the true mean with probability at least 1 minus delta. And in this talk, you should be concerned about situations where delta is like really, really small, like exponentially small in the dimension, for instance. And so this sounds like a fairly fundamental question. So let's see what kind of estimators you can use. The first estimator that you would try to use, since it's a mean estimation problem, is the empirical mean. So let's see what kind of rates we can get. So the first kind of rate is an asymptotic rate, as the number of samples n tends to infinity. In this situation, the kind of recovery guarantee that you can expect is that you can expect a confidence interval which is of the radius root d over n plus root log 1 over delta over n. And this is optimal for Gaussian, so you really can't expect to do any better than this. But on the other hand, in a finite sample setting, the best recovery guarantee that you can expect is root d over n times 1 over delta if you apply Chebyshev's inequality to the empirical mean. And unfortunately, you know that the Chebyshev inequality rate is also tight for certain classes of distributions for the empirical mean. So let's see how these two rates compare. The first thing you notice when you move from the asymptotic central limit theorem rate to the Chebyshev rate is that your dependence on the failure probability delta degrades from being logarithmic in 1 over delta to being polynomial in 1 over delta. And the second thing that you notice is the term that depends on the dimension d and the term that depends on the failure probability delta are additive for the central limit theorem rate, but they're multiplicative for the Chebyshev rate. And now the question that you might want to ask is like, can we actually obtain the central limit theorem type confidence intervals in a finite sample setting? And the somewhat surprising answer to this question was shown in like this amazing paper by Lugosi and Mendelssohn, where they showed that as long as delta is not exponentially small in n, there is an estimator that achieves these CLT style error bounds. The one drawback with this estimator is that we don't know a polynomial time algorithm to actually compute it. This was addressed in another recent breakthrough paper by Sam Hopkins, where he showed the first polynomial time estimator to achieve these CLT style error bounds. But unfortunately, the exponents that show up in the runtime analysis of this algorithm are kind of slow. For example, in the canonical setting where delta is e to the negative d, the runtime is O tilde of nd plus d to the 28. So we proposed a new algorithm for the same problem, which achieves like similar CLT style error rates with a reduced runtime of nd plus d to the 3.5. This is again in the same setting where delta is e to the negative d. Okay? So let me just go over how one actually begins to construct these kinds of high probability estimators. So all of these estimators are part of a general framework called the median of means framework. Conceptually, the idea is really, really simple. You start by dividing your data into k batches. So here you have x1 till xn over k in the first batch and so on. And then what you do is that you compute in each batch, for each batch, a local estimator of the mean. So you have mu hat 1 to mu hat k. In this case, the local estimator is simply the empirical mean. And then you have to figure out some way of like combining these estimators to derive like a final estimate. Just to see that this framework makes sense, notice that if I set f to be the empirical mean of the local estimates, you recover the empirical mean as an estimator. But this estimator is somehow not robust to situations where one of your local means is really, really bad. So you'd want somehow to design a function f which is resilient to these kinds of situations. where a local estimate can be somewhat bad. And this is precisely what Lugosi and Mendelssohn did when they designed their median of means tournament estimator, which was the first one to achieve these CLT-style error bounds. I won't formally describe the estimator here, but just describe the geometric ideas that underlie its construction. And it's based on the following geometric fact. So what it says is that for every unit vector v, the projection of the true mean along the direction v is close to the projections of most of the empirical means. So 0.9k of the local estimates mu hat I, up to an additive error, which is basically a constant times the CLT rate. And this holds for all unit directions v. Pictorially, it's represented by the figure on the slide. What it says is that if you consider this, this slab here with normal vector v, with thickness a constant times the CLT rate around the true mean mu, you'd expect around 90% of the local estimates to fall within the slab here. So it should not be immediately obvious why this fact is true, but we'll only need this to show how we construct our estimator for the same problem. And to do, or at least to gain some intuition there, let's just consider a simpler problem of trying to test whether a candidate point x is far from the mean. So I have a candidate point x here, and it's somewhat far from the true mean mu, and I want to certify that it is in fact far. So let's just denote the vector going from x to mu by delta, capital delta. From the previous geometric characterization, I can certify that x is far from the mean if I can find a direction v so that most of your local bucket estimates are far from x along the direction v. And this is simply a consequence of the characterization of the median of means tournament estimator. And so written down as a polynomial optimization problem, I'd want to solve this problem of finding a unit vector v such that for most of the local estimates, their projections along the direction v are farther away by r. So most of the local estimates are far from x along the direction v by at least r. And you'd want to solve this program for the largest possible r for which you can get a valid solution. So this is a non-convex problem. So this is not the problem we solve in the paper. We instead work with a convex relaxation, but we show that essentially the same conclusions hold in this scenario. So now ideally, you'd want this vector v, this certificate v, to align with the vector of your deviation, which is delta. And if that is the case, then you can perform like a gradient descent type step, and you'd get a better estimate if you could just do this in a recursive fashion. And that is essentially what we show in the proof of our theorem. We show that if you're suitably far away from the true mean, then this value r that you get via solving this program is a good approximation of the true distance of your current point to the true mean. And under the same conditions, you show that this vector v that you get from solving this program also has strong alignment to the unit vector along the direction of delta. And then it turns out that these are the only two properties that you need to run a gradient descent style algorithm to get exponentially fast convergence. And this also holds true for the convex relaxation of the problem that we spoke about previously. And yeah, so that's it for our presentation. Please come to our poster.
We have time for a couple of questions when the next speaker steps up.
Yes.
Problem becomes much easier if you allow them all. This is the dependence on the log of monitor delta instead of just the additive.
Oh yeah, so I think here the interesting part is that you are able to get tight upper and lower bounds for a fairly fundamental problem. But if you would just want to get multiplicative dependence on like log 1 over delta, there are lots of ways of doing that. Yeah.
Maybe, yeah, one more question.
Yeah.
You have these ID samples and you class them into KK categories.
Yeah.
And those would be kind of arbitrary.
Yeah.
Suppose you consider all possible systems. Is there a definition like that?
I'm not sure. Sorry. Yeah. Yeah, sorry.
Let's thank the speaker again.